Yes, good evening once again. So we started our discussion 2 days ago on t-test, and we have gone through one sample t-test and independent sample t-test. The third type is pair t-test. This pair t-test is otherwise known as matched pair t-test or dependent t-test. You know, the other one is called independent, but this one is dependent. So it is used when there are two experimental conditions. Those are possible way you can use it, not as if only one. There are two experimental conditions and the same participant took part in both. Can you see now? So maybe you give them a particular drug for blood pressure. After a while, you measure their blood pressure. Later, you give them another type of blood pressure and also measure their blood pressure some days after. So the issue here now is that there are you take the measurement 2 times on the same group of people. Or comparing means of a measure taken before and after in intervention or experiment, or comparing means of repeated measures taken from the same group in observational study. It doesn't have to be experimental design. It can be observational study. So far, it's not the study design that matter here. It's the way in succession you have two observations, two data sets collected from the same group of people on different occasions, which you are comparing. Or comparing means of peer observation, measurement from the right and left eye, ear, corresponding teeth are also identical twins. So you compare intraocular pressure for right and left, many things between right and left breast, right and left arm, right and left leg, right and left ear, teeth. Think of anything that occur in two in pair in the body. You're comparing measurement mean between the right and left. You can use it for, apart from being used for repeated measure. So at least you know for one person it's two measurements. So that's what it means. That's what, and this formula you've seen it before is very easy. Is the simplest of all. The simplest. You remember our standard error is standard deviation over square root of sample size. I will say that the T, the test statistic, is the difference you are looking at divided by the standard error. So by D mean of the difference you are looking at over standard error is standard error of D, a standard deviation of D over square root of sample size. Can you see? By D, everything over standard deviation over square root of sample size. So you can use it's very simple. This is simplest of all. So now look at an example. The table below shows anxiety score before and after counseling of 9 persons prior to disclosing to them their HIV status. Did the counseling significantly influence their anxiety score? So you see, there are 9 people. The first column is the serial number just to show you there are different people, 9 people. Then the second column is the score before counseling. You know, there's a special tool they administer to them to measure their anxiety level. So they score it. And so before counseling, they score the anxiety. After they have given counseling, they do the scoring of anxiety. So if you look at it for number 1 now, he scored 121 before, now scored 76 after. Number 2 scored 93 before, 93 after. Number 3, 105 before, 64 after. Like that. So this is peer observation. If you look at the formula, you have idea that by D, how do you get it by mean of D? You must find the difference to know the mean. When you find the difference, you find the standard deviation. The D, mean of D, you find the standard deviation. We already know for this one now the sample size is 9. So how do you go about it? How do you know the difference? So you now look at this table now. The first column is still the serial number. The second one is the score before canceling, the one we have shown before. The other one, the third one is score after canceling. So D is the difference, because here now you're looking at the difference, because this score before and after is from the same person for each line for the same person. So you now, okay, what's the difference before and after? You now remove after from before. It doesn't really matter, even if you remove before from after, it will give you the same thing. But logically, you believe that the essence of the counseling is to reduce the anxiety. So you expect generally that even the anxiety should be lower after the counseling. So you can remove the one after from the before. So I will do that now. See D. The one, if you look at number 2, because they are the same, it gives you 0, the difference. So some are positive, some are negative. If the canceling, the score after is higher than before, so they give you negative score. So now that's D. The D now, you can actually calculate the average of the D now. So if you add all the D together, the difference, and divide by 9, it gives you the mean. So if you look at the formula here, bar D is equal to sigma of D over N, which is the addition, sigma, the base of that column D, you see sigma D, addition of the D is equal to 300. If you add them together, it give you 300. You know, it give you the 300. Now, you now divide by the number of observation, making 33.33. So the average is 33.33. Now, you still want to know from the formula, you know that apart from the bar D, which is the mean of D, you need to know the standard deviation because it's part of the formula. So when you have calculated the mean, the way you calculate standard deviation is that you remove mean from each value. When you remove mean of D from D, it gives you this D minus bar D. So when you now square it, D minus bar D square, that's the last column. The summation of it is 4,204. So the variance will be variance of the difference is sigma D minus D square over N minus 1. You know the standard error, degree of freedom rather, degree of freedom N minus 1. So that will be 4,204 over 8 because there are 9 minus 1 making 8. So it gives you 525.5. That is the variance. Of course, you know the unit of the variance is square of the original unit. So for you to bring it back to the original unit, you calculate the square root, and that square root of variance is the standard deviation. So standard deviation is square root of variance, square root of 525.5. It gives you 22.92. So pair T is fair sample T is bar D over standard deviation of D standard deviation of D over square root of N. So making we are calling bar D is the mean of D, which is 33.33 we have calculated over 22.92379, which is the standard deviation divided by square root of sample size. Yes. So when you okay, yeah, I put multiplication there. So at the end of the day now, if we change the formula, change of something division, you now change it to times. It becomes 33 times. That square root of this will come up because that thing, the denominator is 22. That's sorry, the slash is not there. 22.9379 divided by, sorry, it's not there, square root of 9. So when you change it, that becomes 33.33 times root 9 over 22.8. At the end of the day, it gives you 4.362. That is the standard that's the PRT rather, not standard deviation. PRT, that is statistic. Normally, if we are to look at our, go and check statistical table, you will see that if you go back to where, I think yes, the statistical table for that team. I think I show you, yes. So if you look at under 95%, that's the third to the last column. Yes, third to the last column, 95% confidence, 0.05. So you look at the degree of freedom of 8. What is the critical value? You see that it's something like 2.306, 2.306. That's the critical value for T at the degree of freedom of 8. And this one we have calculated is far, far higher than that. It's 4 point something, which means that it's statistically significant. So you can say that there's a difference in the anxiety score before and after. And that shows that the counseling has significantly reduced the anxiety. And if you go and run it, it gives you this. And the funniest thing is that the result is not different from what we have interpreted before. It will show you mean, show you the T. Can you see? But the way it arranges is different from the way it arranges independent T. Independent T, now, if first don't give you 11 tests, there's no need for 11 because there are not two groups now. They give you 11 tests for homogeneity. Now also give you assume if equal variance assume or not, and now give you the T p-value before it come to mean different and the confidence interval. But this one is supposed to give you mean different. Even that mean is actually the mean different because it's different, D, by D, that 3.33, and give you the confidence interval of the different. Also now give you the T statistic, degree of freedom, and p-value. You see that the p-value is 0.02, 0.002 rather, which is very, very significant. Look at the t-value, is like the one we calculated, 4.362. That's just it. So I don't know if there's any question. How do you know if this thing is, without the p-value, you can know if it's significant or not. You see the confidence interval of the difference ranges from 15.713 to 50.954. So it does not cross 0. If it has crossed 0 now, it will not be significant. If it will cross 0, it will the lower limit will be minus something and the upper limit will be plus. Now you are not sure that it cross 0. That is the range of value within which you can find the population difference has included 0. But in this case, it doesn't include 0. So it's statistically significant. If it has included 0, that shows that it's not significant because it means that shows that in the population, the mean can be 0. The difference can be 0 rather. When the difference is 0, that shows that there's no difference. I don't know if there's any question on that. So this thing, okay, approach to in a situation, I don't know why I put this slide here. Approach to normality. How do you approach whenever approaching the problem of non-normality? In a situation where you are already we have demonstrated or we have talked about it before, if the data set does not follow normal distribution, and T is a parametric test. That is that you assume that it follows normal distribution, there is homogeneity of variance, there is independent observation, there is the observation must be at least on interval scale and be independent. But of course, I've said that these things are arranged according to importance. The most important is that we must follow normal distribution, followed by homogeneity of covariance. Then the third important will be at least on interval level. The least important is the independent. And if you look at it, even this dependent T with D, if it has violated it because it's dependent, it's not independent. Because the observation are not independent, because they are from the same people. So that better, we still use it because T statistic or T test is a robust test. And I say a robust test is a test that is still valid when not all the conditions for using the parametric test are met. So in this case, that's why we are able to even use it for it. So what are the issues? Whenever you find out that, oh, maybe there's no homogeneity of variance or it does not follow normal distribution, what will you do? The first thing, and these three options I put here, they are according to importance also. The most important thing is the number one. You rely, that's the first thing you should consider first, if possible. You rely on the robustness of the test. So a robust test, I've already said, is a test that is valid when not all the conditions for using parametric tests are met. So when you rely on robustness of the test, like t-test and other, that can still be valid when not all requirements for using parametric tests are met. But this one, you can still go ahead and still use your t-test, use your ANOVA, because they are robust tests. The second option, if maybe the skewness was so much, the deviation from normality is not there, and to make it worse also, you cannot say there's homogeneity of variance. So when those first two important conditions are grossly violated, you may have to go to the next option. The next option is to use a non-parametric test. So each of these t-tests has its own non-parametric counterpart, which we are going to start looking at tonight. So that's the option. So if the last option, if the second one does not work, is to transform data into a new set of data that are consistent with the assumption and carry out the parametric test on the new data. For example, if something is not normally skewed, it's not normally distributed, you can transform it, logarithm transformation. If you do logarithm transformation, it will at least make it more normally distributed or less skewed. So you make it less skewed so that you can go ahead and now use parametric test. But the problem with transformation, when you transform data, the life is never the same. It's never the same. For example, now if you do log transformation, that log scale, the value in log, whatever you have there, the mean is not an arithmetic mean. It's a geometric mean. So any mean is a geometric mean. It's not arithmetic. You can't talk about arithmetic mean. And if you calculate the geometric mean, and you now back transforming, you have done log before, you now do anti-log. So the value, that mean, geometrical mean, that you back transform through anti-log to original arithmetic scale will not be equal to arithmetic mean. It will rather be equal to the median, the arithmetic median. And you see now, so the transformation is the last option. So most of the time, it's just call the realm of academic. So nobody uses it. So now on few occasions where maybe you think that's the appropriate, but with sincerity, nobody use that. So I don't know if there's any question. That's the end of the team. Let's start discussing. We see after. It's three of those things we talk about. Discuss two before yesterday. This is the last one. So let's look at non-parametric counterpart. At least maybe introduction to it. May not be able to finish it today. By next lecture, we may finish. Non-parametric counterparts of t-test. Sometimes data sets do not meet the assumption required for parametric test to be carried out, and it is not possible to correct the problem of distribution through transformation of data or use of robust tests. Can you see those other conditions? So, in this scenario, we use special kind of statistical procedure known as non-parametric tests. They are sometimes known as assumption-free tests because we make fewer assumptions about the type of data on which they can be used. Most of the non-parametric tests work on the principle of ranking, that is, finding the lowest score and giving it a rank of 1, then finding the next higher score, giving it a rank of 2, and so on. Just rank. Just irrespective of the condition, you arrange the score in ascending order, and now rank it 1, 2, 3, 4. If they are out, I will be 1, 2, 3, 4 to 40. Like that. This process just a minute. Okay. So this process results in high scores being represented by high rank, while low scores are being represented by low rank. Yes. The analysis is carried out on the rank rather than the actual data. You're going to see the way it works. So it's a very simple, logical approach. Now, this table is just us to look at t-tests and their non-parametric counterpart. For example, now, when you see purpose, comparing a sample mean with a population mean, that's one sample t test. We did this yesterday. So the non-parametric counterpart here, Wilkinson sign rank test and sign test. Those are the non-parametric counterpart and use instead of one sample t test. Then we have when you compare means of two independent groups, that's independent sample t test. The second one we look at yesterday. The non-parametric counterpart are Wilkinson rank sum test, Mann-Whitney-U test, Kendall's test, and median test. You see, Wilkinson appear in both, but they are different. That first one is Wilkinson sign rank test. This one is Wilkinson rank sum test. Then test based on the different in pair observation, that is the one we did to the pair sample t test. So the counterpart are Wilkinson sign rank test. Can you see? That's the one you use for one sample t test was what you also use for a pair sample t test, Wilkinson sign rank test. While Wilkinson rank sum test, what you use for independent sample. You also use sign. Can you see now? Wilkinson sign rank test or sign test. So the same thing, the same condition go for pair t test and one sample t test. It's only the independent sample that is different. Now let's look at some historical background to this non-parametric counterpart of t-test. Wilkinson test, first developed by Frank Wilkinson, an American chemist in the year 1945. Look at him. Henry Mann and Donald Whitney in 1949 and 47, then popularized by Sidney Seger, 1956. That's the way. Is this man that first for this, the one you are seeing the picture? Then the other one, see the Henry Barhoudman and Ronald Ransom Whitney now work on it to improve on it. You will see when we start discussing them, see how the improvement came about. Now, the non-parametric test we are looking at, we already said sign test, a type of median test, Wilkinson sign rank test. The sign test used only in direction. Okay, we are starting with comparison on one sample from a population. That is when the situation, the fair yesterday when we said that, okay, one sample t-test. So if you don't want to use, we are not using it because it does not follow normal distribution. The non-parametric counterpart, we already said the sign test. or Wilkinson sign rank test. So the sign test use only directional information. The Wilkinson test use both directional and magnitude. So we make it more stronger. The Wilkinson sign rank test is superior to the sign test. But the sign test just use direction, whether it's positive or negative. That is this one higher than this or not? While the magnitude also come into place with Wilkinson test. Does the Wilkinson is more powerful statistically? Yes. Example, let's look at an example. In a law college, it's random sample of 10 students. Mark, 10 students mark is noted below. Is there evidence that at 95% confidence level to suggest that median mark is greater than 67? Are you see now? They are trying to say, okay, they're trying to compare the median, that is, maybe in another college, maybe the median is want to see this one, is it the same thing also? So you have not calculated the median for this one, but you are comparing this one with the median of something somewhere. You're like one sample test. So look at 10 of them, student number 1, 2, 3, then the mark, these are the mark. So in computing the step in computing Wilkinson statistics, you calculate the difference. So the difference between that 67 and each of these marks, that's what you are calculating. Ignore sign. First of all, ignore the sign. You know what you mean by sign? That when you calculate the difference, you see that if you remove 67 from something, those ones that are less than 67 will give you negative. Those ones that are more equal to 67 will give you 0. Those ones that are greater than 67 will give you positive. So positive or negative sign around the difference. So you rank the distance from smallest 1, you rank it up. Separate the positive and negative rank. Look at it. So look at it. The first one, we first of all look at the different, the first table up. We look at the different, look at the different. The different, some are positive, some are negative. You now forget about whether positive or negative. You try to rank. Look at below, look at the rank. Look at those score. In the second table now, we put the difference irrespective of the score now. We now rank them. So the smallest here is 2. We now put the rank of 1. The next one is 3, give it 2. The next one is 4, we give 3. The next one is 5, we give 4 as a rank. The next one is 7. Can you see? We give, hey, forget the other in minus 7, is 7, we give 5. Can you see? The next one is 8, we give 6. The next one is 9, we give 7. The next one is 12, we give 8. The next one is 15, we give 9. The next one is, the last one rather is 27, as the highest in value, we give 10. So now, after you are done that now, the last table now, you now separate, you now sum, okay, the rank that are positive. Want to sum them up. The negative rank, sum. Or you can say you very separate it. Separate the rank that are. So you know that the difference that are negative are these 27. We look at the second table. 27 and 7. And you see, those are the ones that are negative. So what is their rank? This 27, if you look at negative rank, this 27 is rank number 10. This is minus 7. This 7 and minus 7 is rank number 5. The other one, the majority, they are positive. Look at their rank. So it's just for you to now add them. When they add them together, you see that for the negative rank, there are 15. The positive rank, there are 40. So look at the sum of the rank, positive rank, and add it together is 40. sum of the negative round is 15. The smallest value between each of them, either 40 or 15, is 15. That is the test statistic. Can you see? So that is the test statistic. And I told you one time that the statistic normally, as it's becoming more significant, the value should be bigger. But you know the p-value, which is the probability of making type 1 error, as becoming more significant, it will be smaller. P-value smaller than, as this p-value becoming smaller, is becoming more significant. That's so that the statistic move in opposite direction with the p-value. And when you say, oh, it has increased, it's across the critical, it's higher than the critical value, of course, the corresponding p-value will be less than 0.05. But the exception, I said, are the non-parametric counterpart of t-test, or this one. Look at it now. The smaller, the more. So here now, the cutoff, if you look at the sample size 10, look at the table, the statistical table for that Wilkinson. N is the sample size, because the sample size for this one is 10. So for sample size of 10, the critical value is 11. And this one is greater than 11. It's not significant, because for it to be significant, it should be less than 11. So interpretation is that since the test statistic value is greater than the critical value, hence accept the null hypothesis. They say there's no difference. So there's no significant evidence that the mark median rank is greater than 67. Any question? Any question? Should we continue? How many of us? Should we continue so that we still have the studying the rest? Should stop here so that we continue the rest. You know, we just finished any rest one. Today. Any question? If you are talking, you have to unmute for me to hear you. You have to unmute for me to hear you. No answer. Let me pause.